Okay, we are just about at time, about 11:45 here in San Diego. I will give everyone just a few moments to get back to their seats, get set up again before I hand it over to Bjoern. Excellent. All right. We are definitely at time. So I would now like to introduce Bjoern to present an overview of the analysis resource. Thank you very much, Bjoern.
Thank you, Nina. Okay, so I will present an overview of the analysis resource. And similar to what Alex did this morning, this is meant to be like a broad overview of all the things that we are dealing with in the analysis resource. And I'm actually specifically going to talk about the prediction tools. And Alex is going to follow up and talk about the analysis tools. And the main focus on the prediction tools is going to be actually tomorrow, where we're going to go into much more detail and hopefully going to provide you, here a brief overview of what we have, and then most of the questions hopefully will be answered tomorrow in more detail. But we found that many people come to the IEDB for these types of tools. Actually, let me try to put on my pointer here. So there's three major classes of tools. One is the T-cell tool. So this is anything that can be used to identify T-cell epitopes and predict T-cell epitopes. B-cell tools, similar, anything that can be used to predict B-cell epitopes or antibody binding epitopes. And then analysis tools are not prediction tools. They're meant to analyze sets of epitopes that you have from one way or another and provide additional information, allows you to work with them, identify additional properties that these epitope sets might have. So I'll today talk a bit about these tools primarily, and as I said, Alex is going to talk then about the analysis tools in more detail immediately following this talk. So the prediction tools that we have are applied for a number of things, including vaccine development, but also monitoring of cancer neoantigen responses in trials and checkpoint blockade studies, etc., as I mentioned before. All of the tools that we have are based on machine learning in terms of the prediction tools, or actually the most recommended tools we have are all based on machine learning, which means they take experimentally derived data such as MHC binding data, eluded ligand data, T-cell assay data, and try to extrapolate from those. So basically, we have these sets of data that we catalog in the IEDB, where you have sets of peptides and their restriction, and then you have, say, in the case of MHC binding data, like a measured affinity. And then we use those to generate an algorithm that can take a new set of peptides and alleles and make a prediction what the outcome would be if we were to do the same kind of experiment, in this case MHC binding, on these. So how do you get to the IEDB analysis resource? So you can go directly there by typing tools.iedb.org, and that brings you to this website. Or when you are on the IEDB homepage, you'll see on the right-hand side, there's this panel that gives you the T-cell epitope, B-cell epitope, and analysis tool links directly to go there. When you arrive on the site, you have this overview panel again, which again shows the T-cell, B-cell analysis tools, or you can go to these tabs where each of these are listed individually, where all of the tools are accessible. But I do want to point you here to these other tabs on the right, where we have additional features available. So specifically, you have a tools API. So the tools can be run from your computer directly through a web-based RESTful query. That's the tools API, but you can also download them and run them essentially locally on your computer. And I'll explain that a bit more. And these tabs then give you more information about that. We also make the data sets available that we use to train and evaluate the performance of different prediction algorithms. Finally, as throughout the main website as well, we always have these help and contact links down here. And we very much encourage you, if you run into any problems, please let us know through these centers. We do strive to get as much feedback as possible from our users. And if you're struggling with something, we want to know so that hopefully we can fix it. So starting with the T-cell epitope predictions, this is kind of the overview side, and then they're separator and MHC binding, processing, and immunogenicity predictions. And tomorrow, again, I'll talk about more details, sticking to MHC binding for now as the example. This is kind of how the main interface looks like for most of the tools that we have. The first thing that is being input here is the sequence that you want to scan for potential MHC binders. You can also have lists of peptides here. And then the next thing you can do is to select what method you want to use for your prediction. And as you see here, there's a lot of methods to potentially choose from, and the common question is like, which one should you choose? And the way we answer that is that we perform benchmarking methods, and this is the last big benchmark we did on MHC class 1 binding predictions applied to identifying epitopes, where we compared a large number of methods, and you have here these true positive over false positive rates. You want to have methods that go up here, give you all the true positives before the false positives start trickling in. And in this last large comparison, what we found was that the net MHC pan 4.0 ligand predictions, and again, I'll talk about that tomorrow, performed the best in this comparison. So that made it the IEDB recommended method. That was more or less recently updated. We had a different consensus-based approach before, but this one beat it. So this is what happens over and over, actually not that frequently, but when we have consistent, solid evidence that a new method is better than what we've recommended so far, we switch it out and use that as the IEDB recommended tool. So when you select that, you have to also select the MHC allele that you're predicting for and the length of peptides you're considering. And then you can also specify an email if the prediction is very large, it might time out otherwise, and then that allows you to get an email result back to you before your server times out. And this is the kind of results you're getting back. And again, for all of this, I'll talk about in much more detail tomorrow. But the basic idea is you get kind of like an echo of what your input was that you had, and you have your results here where the individual peptides are listed and their alleles, etc. And in this case, the score column is really what ranks the different prediction outputs that you got. And in this case, for this method, a high score is a good binder. That can often be confusing, different methods. Some consider low score good, like in a rank, you want to have a low rank. But in this case, you want to have a high score. Okay, so the very same thing is there for class 2 binding predictions, where you can have the sequence, there's the method selection, etc. And it's broadly similar to what I showed you for MHC class 1 before. The next method that we have implemented was actually, as you kind of saw in the last one, you're actually left with like a large number of tables to interpret when you do your prediction results. And there's a number of additional steps that we found that we are routinely using in the lab when we are using prediction methods. And so we've kind of tried to integrate the whole workflow of T-cell epitope candidate predictions in this TEPA program that essentially guides you through a number of steps and asks you questions that then allow you to make the final predictions. So here again, you enter your sequence, and we're going to show this next time, but in the end, there's a number of steps in here, like, for example, you don't want to make every single peptide in there, but maybe you want to do 15 mirrors overlapping by 10 that span that sequence, which is much more cost efficient than testing all possible peptides, and that makes sense for class 2. And then you do conservation analysis of the input peptides in a set of other, say, if you're looking at viral isolates, how conserved they are, etc. So this is integrating a number of these steps and then give you like an integrated output. Then like you get a single peptide back and say this might be your best choice here, and can get different kinds of exports. So for the B-cell tools, we have the main categories being linear and structure-based predictions. And I'll go through each of them quickly. So for the B-cell epitope predictions that are linear, the main tool that we've been using for a while is BepiPred, which is essentially like a machine learning method again that has been using a number of different scales and representations of amino acids to essentially scan the linear sequence of a protein and identify segments with consecutive residues that are falling, that have properties that are associated with being an epitope. So there's actually a BeppiPred 2.0, and that is now the also the default choice. And when you run this prediction, you're getting, first of all, a graphical output back that shows you essentially as you go across the sequence, you're getting higher and lower scores, where the regions where you have like consistent scores above the threshold specified, which is like 0.35 is the default, are segments where you are predicted to have more likely epitope candidates. And then you're getting these predicted peptides back as well. You can modify these kinds of inputs, like in this case, this considers like a center position of 4, meaning that you have within a stretch of residues, you're considering the 4th position to be the center, and then it uses that to calculate your overall scores as you move along here. And you can adjust these, including also the thresholds that move these things up or down, and that will change the outputs down here. There's a number of additional scales that we had implemented for amino acid-based property predictions of B-cell epitopes that were described in the literature as being predictive of antibodies. These are mainly as a historical reference. So many of these things were in active use for a long time, but then the BeppiPred methods have pretty much overtaken the others in terms of usefulness. But still, it's interesting to know what people would have done using these past predictions in the past. And there's a number of approaches out there that are combining the different kind of scales that you're getting to get an overall better performing score. Am I hung up? That would not be good. Huh. Can you guys still hear me?
Yes, we can still
okay.
And see you, Bjoern.
Okay, that's interesting. So yeah, now it works. I don't know, somehow it froze on me. Okay, let me get my pointer back here. As we all know, proteins aren't really linear stretches of amino acids, but they form a 3-dimensional fold. So residues that are not close to each other in the linear sequence might very well be close to each other as the protein takes its functional structure. So that has been long recognized, and there's a number of tools out there that are essentially taking advantage of the structural organization of amino acids in a protein, and then trying to find properties of patches that might be recognized as an antibody binding site. So in this case, this Epitope is, I think, the first tool that we had implemented on the IEDB that does this, where you then have to have a PDB structure for the solved protein, or you can supply your own homology model of it and then run an antibody prediction through it. You'll get a similar output on the linear scale range as we saw before for BeppiPred, but you can also see these are not the individual residues. You can also see these in a 3D view projected on the structure, where you then see which parts of the protein are likely to be recognized by antibodies. So as I mentioned, we have these standalone tools. So you can download these and run them on your local machine. The advantages are that you don't need any internet connection, and specifically if you're sending back and forth large data set, internet connection itself can actually be limiting. So specifically, as I said, if you have very large data sets, so I mean, we ourselves, if it comes to large analysis we did for like metaproteomes of multiple mycobacterial species, we do run these offline because the server would just crash under the load of requests. These are free for nonprofits and academia and available for industry at a nominal fee. If you're interested in any kind of licensing of these tools for commercial purposes, please contact us at license@iedb.org. The whole website, as I should point out, is always free. The reason why we are doing licensing for the downloadable tools is this is actually something we hadn't necessarily planned to supply, but industry has been specifically asking for to be able to work behind the firewall on their specific tools. So the output of these standalone tools looks very similar to what we have on the website. None of this should come as a surprise, but you can run these then simply as a command line tool where you're providing a sequence file as an input and the kind of parameters that you other specify on the website as command line parameters. And this is the kind of output you're getting. You can also run the same kind of programs through an API, meaning an application programming interface. So their requests are directly sent to the server at LJI. You don't need to install any tools on your machine. This is completely free, available for all users again. This can be incorporated into prediction pipelines. So if you have like a set of steps running, getting into your predictions, this would be one where you then just call our server to get your results back. And one of the biggest advantages here is, like, as we are adding new tools and new versions of tools in there, you don't have to reinstall and see if things works again. It should keep on working out of the box. This is the examples of the kinds of tools that are available and how to run them. And then here's an example of how you can integrate calls to these tools into your existing code. So this would be how you, as an example, implement a Python command that predicts the binding affinity for a given peptide allele and length by doing a curl call that essentially goes to the tools cluster for the IEDB and will then gives you the result back. And then you can get the same kind of output format that you get from the website or get from the standalone tool. But then the only thing you need to do to change the method used is you change that string here and you're done. So that was summarizing the three options that we have available. You can do direct predictions on the web, which is definitely the most convenient. I would always start with that. You can, if you want to do very large sets specifically, you can run them on your standalone. You can do calls to the API that I just demonstrated. And there's different advantages and drawbacks of the different tools that I believe I went through as I talked about the three options here. So to summarize the prediction tools, one of the first things we always should point out, so the prediction tools, again, are trying to generalize from the data that we've collected in the IEDB. Now, the best thing you can do is not having to run a prediction tool that generalizes on the data, but you look at the data. So very often we've had people who are working in a certain area and say, well, nobody knows any epitopes in my specific virus. So, well, first, please look if there really isn't something out there. There's nothing better. The one thing that is clearly better than a prediction is real data. Then again, like, these prediction tools are based to extrapolate from existing data using machine learning algorithms to identify essentially patterns in the data that we have and generalize them. We're using RC curves and AUC values that were the graphs that I showed you as performance metrics that we're using them to rank the different methods that are out there. Prediction, we have to point out, is a screening step. Some people are saying, I ran this tool and I have this peptide coming out, and so it is an epitope. That is not the case. You have a candidate, and a given predicted, say, binding affinity or immunogenicity needs to be experimentally verified. Otherwise, what you have is a prediction, which is perfectly fine, but it's not sufficient. Then the analysis tools, which Alex is going to talk about next, are going to helping you to examine existing sets of epitopes to gain new knowledge. Those do not have really performance metrics. Their performance is usefulness. There isn't necessarily like a right or wrong or like better or worse. The better or worse is in the usability, and they have a broad range of applications, and Alex is going to go into those. And with that, I'm done. I think I'm way early.
You did wrap that up efficiently. Thank you. We are a little bit early, but that just means we'll have more time for the Q&A and for Alba and Alex's presentation. So thank you very much, Bjoern.